Good afternoon. So let us start today's lesson. So if you remember, uh, we talked about permutations actually quite a lot, and then we learned about R permutations, and then we last time we started talking about combinations or R combinations in which the order of the items are not important for us. And we solved some problems related to this. And then I want to continue solving more examples and more ideas on combinations today. Okay, so for warm up, let us solve some problems together. So example 1, consider the lines L1 and L2 that are parallel. We consider 6 points on L1 and 8 points on L2, so let me just draw a diagram. So here I have two parallel lines, yes, and then I have 6 points on L1, so let me call this one, for example, so let me call this one, for example, L1 and this one L2. I have 6 points on L1. So 1, 2, 3, 4, 5, 6. There are 6 points here, and then we have 8 points on the other line. Yeah, just there are points. There are no specific rule for them. So 1, 2, 3, 4, 5, 6. I don't know, 7. And for example 8. So here we have these 8 points here. So using these 14 points as vertices, how many triangles can one draw? So for example, this is one possible triangle that I can draw. The vertices are these 3 points. Another triangle I can imagine is this triangle. Again, the vertices are this. Another possibility is to have this situation. Yes, this is what I mean. This is 1, 1, and 1. This is another triangle. So how many triangles do you think I can draw if I want to draw it in the way that I just described for you? So how should I start counting it?
Consider two cases. One is where the two vertices are on L1 and the other one is where the two vertices are on L2.
Yes.
There are 2 on L2, then there must be 1 on L1.
Yes. Okay, that's one possibility. So let me call this method 1. Okay, so what Alex is saying is that we categorize these triangles into 2 types of triangles. So one vertex to be blue, 2 vertices be red. This is one type of triangles that you will have here, or the other way around. One vertex to be red, 2 vertex to be blue, and they are not confusion between them. There is nothing in common between these 2 type of triangles. Yes, so I would say that I will take 1 blue, 2 red. So in how many ways I can choose 1 blue? By the way, is this problem a combination problem or a permutation problem? So make this clear. Let me, for example, give you this A. So let me make it clear. So let me call this one A1, A2, A3, A4, and A5 and A6. Yes, and the other one, for example, let me change the name. B1, B2, B3, B4, B5, B6, B7, and B8. So do you think that this is a permutation problem or a combination problem? To answer this, you need to convince yourself in this way. For example, I choose 1 point from the blue ones and then choose 2 points from the red ones, and that is it. I don't face permutation because I don't care how I order the vertices. This triangle is the triangle you see in the picture. If I name it in this way, it is also the same triangle. Even though from permutation point of view this is a different permutation than that, but in this problem, in this context, they both refer to the same triangle. So this means that I'm not facing a permutation problem, I'm facing a combination problem. Okay? So then it means that if I want to count the number of these type of triangles, one vertex blue, two vertices red, okay, so I would say that either I have one blue vertex, I choose 1 point from the blue ones, I choose 1 point from the blue ones, and I choose 2 points from the red ones, or I choose 2 points from the red ones and I choose 1 point from the blue ones. So that should be the answer. This is not very hard. Let us calculate that. So I will teach you, there are some ways that for these numbers you can do it simpler. So this is definitely, by the way, what is this number? Instead of choose 6, choose 1. What can I write immediately? Not by calculating factorials or whatever, because you remember we had a formula for this. It was this formula. We had it before. So I don't want you to use this formula, but immediately you know what should be the answer. What's the answer?
Just 6.
Just 6. I have 6 points and I want to choose one of them. Definitely there is only 6 ways to do that. You can also confirm that using the formula. But this one becomes 6. The other one, if I calculate it using this factorial formula, it becomes 28. And then the other one becomes 15. And then the other one becomes 8. Now if I calculate this, 120 and 168, and the other one is 80 and 120, so this becomes 200. I'm intentionally calculating this, but for the exam most of the time that's enough. I want to calculate it in a different way. Do you have any other strategy to solve the same problem? So can you think of using complement rule in some way? Of course, I'm not saying that is better, but I want you to think different ways to understand combinatorics better. What do you think? What's the problem if I write it in that way? I don't know if this gives us the right answer. So 14, 3. So do you agree with this answer?
No, because it can happen that 3 points are chosen on the same time.
Exactly. So if I write 3 from 14, it means that I am also considering the cases that all 3 of them are being chosen from this, or all 3 of them can be chosen from this. But of course, if all 3 of them are chosen from here, they don't make a triangle for me. So this is not 100% correct unless I subtracted not the one that I don't want to from it. So how can I calculate that? What are the undesired items that I want to remove from this if I calculate it in this way? So can you tell me minus what? And pardon? Just give me formula so that I can understand.
Minus 6 over 3, or like
6 choose 3, yes. It means that I am choosing all of them from the blue ones, minus again.
8. Minus 8 chooses
3. Yes? Okay, so yeah, let us save time. I use my calculator to calculate them. Hopefully, if I haven't done anything wrong, these two should give the same answer. Let us check. So 14, 3, minus 6, 3, and then again minus 8, 3, yes. I don't know, so what happens to this calculator sometimes? Sorry, 14, 3 minus 6, 3 minus 8, 3. Yes, the answer according to my calculator is just 288. So you see, the first method was simpler actually, but it is also good to solve the problem in two different ways. Any questions so far? So this is important to realize if the problem is a combination problem or a permutation problem, yes? I think this problem is also nice. I don't know, I want to finalize this, but let me just give you at least 2 or 3 minutes to think about this problem. In how many ways, let me just make sure that you understand the same thing that I want to transfer to you. In how many ways can 10 people called A1, A2 up to 8 sub 10, can 10 people stand in a queue such that A1 and A2 are both ahead of A3, A4, and A5 all? So it means that, I don't know, these 10 people are standing in a queue. My goal is to say that, okay, A1 and A2 should be coming before A3, A4, A5. I don't know how they are standing. But I know that there is a border that on one side you see A1 and A2. On the other side you see all these other people. I want to see in how many ways we can order them. Of course, there can be arranged in 10 factorial way, but I am interested in these possibilities, okay? So I pause the video and then I want to think about the problem and just try to give your ideas about that. The strategy for the problem, because as you saw probably, I want to teach a little bit more today. So any ideas how to solve the problem?
I mean, we could draw a line and then say that everything to the left of this line can either be no, wait, that doesn't work.
I don't have any idea. Might be the line is also okay. What did you get any number out of it?
No, because I realized that it would be a very long expression and I didn't want to type it into my calculator, so I see if I had the wrong strategy.
Okay. Anyone else? You see, this is the nature of the problem. If I solve the problem, I think it should be easy for you to understand it. Okay, I can start solving it by drawing these. So I have 10 positions in principle. Yes, I want to have 10 positions for these 10 people. As I am drawing, you still can think, yes? And think about that. I have 5 people who I have to respect something about them. And then these 5 people definitely at the end should occupy 5 places, yes? 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So I have 10 positions. These positions are supposed to be occupied by these 10 people. And of course, some of these are acceptable for us, the ones that actually respect the condition in the problem, the other ones are not. Okay.
I have a new idea.
Yes, just please let me know.
What if we start by writing out A1, A2, and then followed by A3, A4, and 5, and then we put like circles between them and insert number after number, and then into these spots, right? And then for each time we do it, we also increase the number of.
Okay, but saying something is different from just calculating it. Might be this is just a rough idea, and if you sit down and figure this out, it might work, I don't know. But as you see, this time I decided to draw all the 10 places because the way that I was thinking about this, I would say that there are 10 positions. Definitely these people A1 and A2 together with A3, A4, and A5, this is clear. They should occupy 5 positions out of these 10 positions. This is clear. So, and then what I do, I will choose 5 positions out of these 10. I am choosing. Choose means that I am labeling them by a cross, not different labels. So for example, I would say that I will take 5 of these positions. I am choosing it. What is the meaning I am choosing it? It means that I take my pen, I cross it here, cross it for example there, this where, 1, 2, 3, 4, and then for example this very last one. This is the meaning that I have done. In how many ways I can put these red crosses on top of these positions? This number of ways. Why this is a combination? Because if I interchange 2 crosses, I don't recognize that. So the order is not important. The combination is important. If instead of this cross, I keep the crosses the same, but instead of this one, I put the cross here, you immediately recognize the difference because the combination of these crosses has been changed. So just putting crosses on top of these positions is just a combination problem. Now, this is clear. These are the positions that I want to fill them up with these people, A1, A2, A3, A4, and A5. Just momentarily in your head, forget about these positions that are not crossed. Just highlight these positions in your head. And then I am giving you these people, and then I want you to arrange them in the way that we are supposed to arrange them. Okay, so which positions you will take for A1 and A2 and which positions you will take for A3, A4, and 5, it becomes very clear now. The first 2 positions should be definitely occupied with A1 or A2 in one order or the other, and these 3 positions should be filled with these other 3 people. Yes? Is that clear? I cannot do anything except that. If I don't do that, if I don't give these 2 positions to A1 and A2, and if I don't give these 3 positions to A3, A4, A5 in a permutation way, it means that I will actually not respecting the condition and the problem. If I want to respect the condition of the problem, definitely these 2 positions have to be occupied with A1 and A2. So in how many ways these 2 positions can be occupied with 2 people? It becomes 2 factorial. And now the next 3 positions, the next crossed positions, they should be filled with A3, A4, and 5, and that is 3 factorial. Okay, now I hope that you agree with me. Now for example, let me just change my color. I decided to put A2 here, A1 here, and here I decided to put I don't know, A4 here, A3 here. Let me put A5 here and A3 here. So you see, this is exactly one of those combinations that I am looking for because the border is here now. Before this border, I see A1 and A2. After the border, I see these 3 people. Okay? So both of these people are ahead, standing ahead of these 3 people. But this 3 factorial is coming from the fact these 3 people can be interchanged by themselves, among themselves 3 factorial way, and these people can be interchanged 2 factorial way. But now I have to occupy these positions as well. But how many people are left now? I had 10 people, 5 of them have already been standing, so there are 5 people left for me, and there are 5 positions for me. So this becomes 5 factorial. So this is the way that I was coming up with this strategy. And when I calculated this number by my calculator, it is this number. So you see, these problems, writing the answer is very simple, and especially when the strategy becomes clear, immediately you can solve this yourself. But cooking up this strategy, it needs a little bit of experience. Of course, if you are interested in these kinds of problems, you need to solve a lot of them. Okay, hopefully at least you understand my strategy. So anyway, if you can think of another strategy, I would recommend you to just think about this, and if you get the final answer as it is, and please let me know about your strategy if you were able to get this one, because that's also very important, very interesting for me to see another different way to solve the same problem. Okay, now let us go to the next problem. So this is an analytic problem. I want you to know how to work with the formula. So let me just write the formula in front of your eyes. So if you remember, we had this formula. NR is equal to n factorial divided by r factorial times n minus r factorial. Oh, I do not have enough space here if I want to write that big. Anyway. Okay, so here, so let me just, oops, sorry, make it a little bit smaller if I can resize it. Okay, so here, now I don't know, this is an equality. I want to show this equality. I think it's always better to start from the side which is more involved and try to manipulate it and simplify it to get the other side. Okay, so I would, but this is why I will start from the right hand side. So I have n minus k plus 2 divided by k minus 2, sorry, k minus 1. Instead of this factorial, I compare it with that formula. N is the same, but k minus 2 is playing the role of this r. So what I do, I write n factorials in the numerator, and the denominator I will write k minus 2 factorials, and n minus r, n minus k minus 2, which becomes n minus k plus 2 factorials. So this becomes n minus k plus 2 factorials. Okay, and then we have to simplify this expression. Okay, I think it's not hard. You can come up with the answer yourself. It's actually much simpler than I thought, so it doesn't need that much space. So here on the right hand side, I need this n factorial, so let us not touch this one. But you immediately realize, what can I write this for short? Can you tell me what can I write instead of these two being multiplied together?
K minus 1 factorial.
Exactly, so that's k minus 1 factorial. But I can decompose this to n minus k plus 2 times n minus k plus 1 factorial, and this one and that one will be gone. So that's good. So let me just do all these things. So it becomes that divided by k minus 1, and I have times n factorial in the numerator, yes, and in the denominator I have a k minus, so let me write, yes, that's good. And then the other one, n minus k plus 2, n minus k plus 1 factorial. And then you see that this one, this one and that one are cancelled. And then what you get is equal to n factorial divided by, I multiply this by that, it becomes k minus 1 factorial. And then after that I have n minus k plus 1 factorial. But you hopefully agree with me. Let me write it in this way. I can write it as k minus 1 factorial. For the next one I write n minus k minus 1 factorial. Yes, because if I multiply the negative sign inside, it becomes negative k, which is the case, and it becomes positive 1, that's also the case. But if you compare this with this main formula, you see that instead of r everywhere, you have k minus 1. You see, instead of r factorial, you have k minus 1 factorial, but also instead of n minus r, you again have n minus k minus 1. So it is clear that this is playing the role of your r. And now if you see, that's exactly the same formula. The only difference is that r has been replaced with k minus 1. So this becomes n choose k minus 1, and that is the right hand side. So one type of problems are of this nature. So you need to be able to work algebra of these combinatorial numbers. And again, Yeah, if you have questions, please let me know, okay? Interrupt me whenever you don't understand something. And there are also another type of problems you are not supposed to. Yes?
Will we get the formula and the exam?
Yes, these formulas are in the formula sheet, yes. These formulas are there, yes. So solve the following equations. So this one we want to solve. I have intentionally used this C so that you get used to be with both notations. So this is just combination again. But here I'm not asking you to prove this equality because this is not an identity to prove. I'm asking you to solve this equation. It means that you are supposed to find n. Okay. So here we have a formula. So let me write both of them here for you. So if you remember, what was Pn and R? It was n factorial divided by n minus r factorial. And then we just write here again in this notation. This is n factorial divided by r factorial n minus r factorial. Okay. Now I want to use these two and solve this problem. Okay, so let me adjust the spacing. Okay, so I start from the left hand side. Instead of Pn and 4, I use this formula. Instead of n, I just put n, but instead of r, I put 4, yes? So this becomes n factorial divided by n minus 4 factorial. That's it. And for the choose n 4, I write n factorial. Again, r is this 4, so I have to put a 4 factorial here and a 4 here. And on the right hand side I have 25 times. Again, I have another combination, but this time r is 5 in this problem. Okay, so I have to start solving this problem. So what can we do? I don't know if you are easy with that. So I think I can multiply everything by. Okay, so let me write it in this way. You see, 5 factorial in your head, you can write it as 5 times 4 factorials. Instead of n minus 4 factorial, you can imagine n minus 4 multiplied by the previous factorial. Previous one is n minus 5 factorial. So if you don't mind, let me write all these things so that you can understand it easier. So this becomes n factorial divided by, instead of n minus 4 factorial in the denominator, I just write n minus 4 n minus 5 factorial. And on the right, and again I will have this, and I will have 4 factorial, and then I will repeat this. You don't need to write that much, but I'm just writing because I want you to see it in front of you. Instead of 5 factorial, I just write this. And then I have n minus 5 factorial, yes? So if you remember, whenever you want to solve an equation with fractions, it's easier to get rid of fractions first. So this way of thinking makes it easier for me to see what is the expression that I have to multiply the both sides so that I can get rid of the fractions, yes? Okay, so hopefully you can see that I need to multiply by this, then I will get rid of this, I will get rid of this, and I will also get rid of this. Of course I will get n minus 1, n minus 5 up there. And by the way, I can divide by n factorial, I think, so that is easier. So let us do that one first. I divide everything on both sides by n factorial. So this becomes 1, this becomes 1, this also becomes 1. Then I will multiply by this expression. If I multiply that, this is totally gone, so what is left for me is 1. If I multiply that, it's 1 over 4 factorial left. So if you don't mind, let me just do it in 2 steps. So this becomes 1. Of course, you can do it also in 1 step. So then the next one is 1 over 4 factorial. The next one would be what? 25 over 5 times 4 factorial. and then I will have n minus 4. Okay, agree with me? Let me explain. So I am multiplying both sides by this expression. So you see, this expression will be gone if I multiply it. So 1 over 1 would be 1. I am multiplying everything by that, so it is 1 over 4 factorial. I am multiplying everything by this expression, but this one and this one are gone. N minus 4 survives, so this is why you see n minus 4 here. And then I have a 25, you see 25 here, and 5 times 4 factorial, you see it here. So everything that I have done is completely correct. So what happens now? I can go further and simplify this 5 with that 25. It becomes 5 times. And to get rid of the final fraction, you didn't need to do it in 2 steps actually. I multiply by 4 factorial everything. The first number becomes 4 factorial. The second number becomes just 1. The third number would be 5 times n minus 4 because I multiplied this by 4 factorial. And this is a very simple equation. I have to solve that. What is 4 factorial? 4 factorial is 1 times 2 times 3 times 4, which is 24. And then add it to 1, it becomes 25. Equals to 5 n minus 4. I divide by 5. And then I add 4 to it. So that is the number that I was looking for. I'm not saying that this is the best way. Might be you can do it in your head much more quicker than this, but that is one way at least. So the number that I am looking for is n equal to 5. But by the way, I have to be careful. Is n equal to 5 acceptable? For example, if I get n equal to 4, this is not if I get n equal to 4, it is not acceptable. Why? Because when I am using these symbols, I am intentionally, implicitly thinking that this number is greater than or at least equal to that number. If that's not the case, this symbol is not defined in the first place. So what I'm saying is that assume that you solve the problem, and at the end, instead of getting n equal to 9, you get n equal to 4. You should be careful, this is not acceptable. And then you would say that there are no solutions for this, because n equal to 4 is not acceptable for this. Okay, so that's also another type of questions that you might face. And then I want to talk a little bit about computing these numbers. I have given you another formula. You might think that I am making things complicated, but believe me, in practice, this is much easier to do than writing that compact formula. So first of all, I want to guarantee that this is the correct formula, and there is a typo actually here. I will change it. So if you don't mind, let me just change it. Okay, sorry, I think I fixed it now. So this formula for this combination, even though it is a little bit lengthier, but I don't want you to memorize this, but I will give you the idea is very simple. First, let me convince you that this formula is also working correctly for NR, for n choose R. So what should I do? I would say that n choose R, we have the formula, it's n factorial divided by r factorials and then n minus r plus 1 factorial. So what we do, we expand the numerator. I write n times n minus 1 times n minus 2 up to times n minus r plus 1 and then n minus r factorial. And then in the denominator, I will have r factorials n minus r plus 1 factorial. So you see that I have started from n, the previous number, the previous number, the previous number, until I reach to this one. I will stop here. Oops, I have made a bad mistake. This is not the correct formula, sorry. This is just this one. I don't know why I have written 1 there. There is no 1 in the formula. Yes, do you remember? We had this formula here. Okay, so now what happens is that you immediately see that this one and that one are gone, and then you get your formula. What I have written here in the numerator is this part, and in the denominator you see only one r factorial is left. So this tells you that if you want to calculate this more or less quickly, you start from n and write consecutive numbers. How many consecutive numbers? R of them, and then divide by r factorial. So for example, let me use to immediately calculate this, or calculate it much faster, not immediately. So 7 choose 3. I write how many, this number that you see is 3. I write 3 consecutive integers, so 7, 6, 5, and then divide by 3 factorial. But we know that 3 factorial is 6, so the answer immediately becomes 35. So this is the way that I usually use it when I want to calculate it more effectively. Of course, if the numbers are big, I cannot calculate. There is not much difference. But for these small numbers, you can use this trick. You see there is a 3 here, so what you do, you put a 3 factorial in the denominator and just write 3 consecutive integers starting from 7, and then simplify that, okay? So good to know about this, even though it is not necessary at all, it's up to you. Okay, but there is a very important theorem. It's extremely important to realize, both from analytical point of view and from a combinatorial point of view, that this number is always equal to this number. In other words, if these two numbers that you see below, the sum of them is equal to n, they are the same. For example, I don't need to calculate to see that. If I have 10 and 3 here, if I have 10 and 7 here, they are equal. Why? Because if I add these two numbers below, it becomes the number on top. If this happens, these two combinatorial numbers are equal. This is also clear from calculational point of view and from combinatorial arguments. And by the way, for n equal to 0 and n equal to n, these are exceptions. Let me ask about this and I will clean that. So what is your guess, by the way, about this number at the end without calculations?
1.
It should be 1, yes, because it tells you that I have n distinct objects. I want to choose all of them. In how many ways I can do that? In one way, I have to choose all of them. So definitely this is equal to 1 without calculation. If you want, you can calculate it using the formula. You will get the same number. And if you remember, we had this by convention. If this number is 0, we define this to be 1 as well. So you see that even in this extreme case, the rule is the same. So this is why you see I have started from 0. Because n and 0, when I add them, it becomes n. And it tells you that as soon as you have this property, these two combinatorial numbers are exactly equal to each other. So this is the extreme case. In most of the cases, this is the case that we want to see. We can understand this problem from two perspectives. One, analytic perspective. So let us just do that. I will start from the right hand side and calculate it using the formula. So what is the formula? I need to write n factorial on top, and then this is playing the role of r here. So I need to write n minus r factorial instead of r factorial. And I have to write n minus the number below, n minus r factorial. But if you simplify that, it becomes n factorial, n minus r factorial, and then if you multiply this negative sign inside, it becomes n minus n plus r. This one and that one are gone, so it becomes r factorial. And then this becomes what? This is exactly the formula. You see that there is no difference between this one, and if I interchange r factorial with n minus r factorial, so that is exactly equal to the left hand side. So analytic proof of this is very simple, but this is a very important theorem. Can you cook up a combinatorial story so that we can realize this without calculations? So for example, let me be particular for you. Can you cook up a combinatorial argument to show that to show that 10 choose 3 should be equal to 10 choose 7. I mean, from combinatorial point of view, this should be trivial. This is a special case of this theorem. But can you tell me, why do you expect that these two numbers are equal even without calculations? So here what you are doing, for example, you can consider 10 people. I want to choose 3 of them to take them with me to a journey. As soon as I choose 3 people to take with me to a journey, it means that I am select. I don't know how. Do you, in English we say deselect, or I don't know. You are deselecting 7 people not to take them with you. So there are a one-to-one correspondence, yes? So if my people are A1, A2, A3, A4, up to A10, as soon as I choose 3 people to take with me, 7 people are left not to take them with me. So there is no difference, yes? So between these choices and these 3 choices, there is a one-to-one correspondence. If I tell you that which people have been chosen to take them with me, you immediately can tell the people who haven't been chosen to be taken with me, and the other way around. So it is very clear that the number of these 2 items at the end should be the same, because when you choose 3 people, it means that you are choosing other people not to take with you, and there is a one-to-one correspondence between these 2 items. So I don't think it should be hard for you to understand from this combinatorial argument that these 2 should be the same, and this works even in the general case. Understandable? Okay, so for example, if I want to solve this problem, if I want to do it a little bit more quicker, if I want to do this, if I want to use the previous problem, previous argument here, I need to write 6 factorial in the denominator, and I have to write 6 consecutive numbers on top. Yes, because 6 appears here. But now I can combine these 2 ideas. For example, instead of 6 choose 8 6, I can write choose 8 2. This I want you to understand immediately, that why these 2 numbers are equal. This is the content of this theorem. This tells you that as soon as you have these 2 numbers that add to the top number, these 2 are the same, regardless of which one you prefer to argue, combinatorial argument or analytical argument. Okay, and then I can use the previous formula. I put a 2 factorial in the denominator, and I just write the product of 2 consecutive numbers, not 6 consecutive numbers. And then 8, this is simply 28. So you see, it's much easier to calculate things if, of course, you want to calculate a little bit faster. And I think, of course, the proof of this is a little bit harder, but I think at this point it is good to know about this. If you see this number is equal to that number, the ends are the same, but these might be different. Of course, I haven't written very carefully, because you know that x should be at most equal to n, y has to be at most equal to n, they have to be natural numbers, assuming that all these conditions are fulfilled. If you see these 2 are equal, there are 2 possibilities, not more. Either these 2 numbers are exactly the same, or, this means or, they add up to the top number. Okay, the proof of this part is very simple. It's very simple, you can do it. The proof the other way around is a little bit technical. But let us ignore that, okay? And just I want you to make things complete, so this is why I'm mentioning it. For example, yes?
In example 6, why did you do 8 times 7? I didn't understand that.
So I told you that in this way that I was describing you right now, So do you remember how did I solve that problem?
Oh yeah, because 2.
Yeah.
Okay.
That is two numbers. If I wanted to, the reason that I'm bringing it up is if you want to use the same rule for this, then you have to write 6 consecutive numbers.
Yeah.
But if you combine these two things together, the calculations become easier. Okay, now we go here and then let us solve one problem using this idea. So you see that two combinatorial numbers like this are equal. Two choose numbers are equal and the top ones are the same. So if this equality happens, it means that this equality happens if and only if this happens or that happens. Okay, so this means that this is equivalent to saying that x squared is equal to 5 minus 4x, or x squared plus 5 minus 4x is equal to 10. So it means that I am left with solving two equations. Okay? And they are connected with or. So let me consider this one number 1 and this one number 2. Okay? So let me calculate solve number 1 first. So I move 4x to the right, it becomes positive 4x, negative 5 equals to 0. You can use ABCPQ formula, but I think the numbers are easy. Yes, we can guess. I need two numbers whose sum is 5. Whose sum is 4 and the product is negative 5. What are they? These are two numbers, yes? So it being equals to 0, then gives me x equal to minus 5 or x equals to 1. But are both of them acceptable? Yes or no? Just talk to me.
No.
Which one is not acceptable?
Minus 1.
Why?
Or I mean, wait, let's see. Yeah, because then you'd be selecting into a larger number.
Exactly. Because if you put minus 5 in the previous equation here, for example, then you get a choose of 10, 25, which is meaningless. It means that I am choosing 25 people from 10. This is not possible. Okay, so this is not acceptable. Not because, of course, it is negative. The negative part doesn't make any role. So even if I put negative number, it becomes 25 positive again. Yes, so but x equals to 1, let us check. This gives me 1, this also gives me 1, so that's okay. So this means that this is one of the possible answers. But I have also another possibility I have to take care of. It means that if I simplify this equation in my head and put it here, x squared is just x squared, minus 4x is minus 4x. I move 10 to the left, it becomes negative 10. 5 negative 10 is negative 5. Again, you can factorize, I think, instead of using PQ formula. Two numbers whose sum is minus 4 and the product is minus 5. So it's minus 5 plus 1 this time. Then I have two options. Either x is equal to 5 or x is equal to minus 1. So which one is not acceptable, or both of them are acceptable? Is 5 acceptable? No, for the same reason. Yes. This becomes 25, or even this becomes negative. So again, this is not acceptable. But x equals to minus 1. Is minus 1 acceptable? Yes or no? Yes. Minus 1 is acceptable. Because if I put minus 1 here, it becomes 10, 1. That's okay. If I put minus 1 here, it becomes 10, 9. And that's also okay. And then, of course, you see that they are equal because they add up to 9. They add up to 10. So it means that I have two answers, plus or negative 1. So this is also an application of this remark in a practical problem. Okay. So everything here is finished, but now we have this formula in the book. It's a very, very important identity in combinatorics, and that's called Pascal's identity. Pascal is I think, French mathematician. I don't remember, but he was a mathematician and physicist. So I think you have his laws in fluids, yes, Pascal's law in fluids. Okay, so here, this is extremely important but very simple. This is the idea. This is called Pascal's identity. What does it mean? It means that if you have a choose number like that, you can decompose it into two parts. But be careful. The number on top that appears on the right is always 1 unit less than this one. But there are two different scenarios for the bottom number. In one of them, you have the same number. In the other one, you have 1 unit less. Sometimes it is useful to understand and go from this direction to that direction, meaning decomposing this into two parts. But sometimes two of them are given, you need to see the pattern and combine them back into the original form. How can I see the pattern? If I have the sum of two choose numbers so that the top ones are equal and the bottom ones differ by 1. If this happens, it means that your pattern is established. And then how do you go here? You add 1 unit to the top number, you get this one. You choose the maximum value between these two and put it as the bottom number there. Okay, but here, before giving some examples related to this, let me just prove it. And I want to prove it again in two different ways, using analytical arguments and then using combinatorial arguments. I think it's both of them. Of course, the combinatorial arguments are more fun for me, but analytic ones also okay. So let us prove this. Analytic method. Okay, so I hope that you agree with me. We should start from the right hand side because it's more involved and then we have more chances to see what's going on. So I will start from the right hand side and then write the formulas. Okay, so I think now at least momentarily you have the formula in your head. So if I want to write this, n minus 1 factorial would be the one on top, and then I have r factorial, and then I have the difference of the bottom one from the top one, yes? Yeah, please let me know. Do you have any questions? I have written this instead of this. Is that understandable for everyone? Using this formula.
Yes.
Okay, good. And I want to do something similar for the second one. Okay, so let me just do this calculation here and I will clean it up. So n minus 1, the top one, minus the bottom one, and then it becomes n minus 1 minus r plus 1. This one and that one are gone, so it becomes n minus r. So what I am going to write here is just n minus r factorial. Yes? Okay, so let me clean this. We don't need that. And now you see on the right hand side I have one single expression, so it means that I need to find a way to make a common denominator between these two. Okay, and I would say that the naive way of doing it is just multiplying it because you are making the problem very hard. But immediately you see that between this one and that one, r factorial itself can play the role of the common denominator because r factorial is nothing except r times r minus 1 factorial. So r factorial is divisible by itself and it is also divisible by that. So between these two, this will play the role of this common divisor. And this one and that two, they are the same, yeah? So the same argument, not the same. So because n minus r factorial can be written as n minus r factorial times n minus r minus 1 factorial. I made a mistake, sorry. N minus r factorial is n minus r times n minus r plus 1 factorial. Sorry, let me write it again. It's better to write it down. So n minus r factorial is equal to n minus r times the previous number factorial. That is my intention, And let me also write r factorial to be r times r minus 1 factorial. So these are the things that you need to have in mind. Okay, now having this in mind, can you tell me what would be the good common denominator? And I hope that you appreciate what I have written here is exactly what appears here. There is no difference between them. Here I have written minus 1 first and minus r second, but that's the same thing. Okay, now can you tell me, if I want to find the common denominator, what do you tell me to write instead of the common denominator? No answers?
R
Yes?
factorial.
Yes?
And then n minus r factorial.
Exactly, thank you. So this is r factorial, because r factorial not only have this in itself, it also have this one in itself. Has this one in itself, and the same thing for this one, as you said. Thank you very much. So it becomes n minus r factorial. But if I want to see what happens in my head, I need to divide this by that. Okay? So let me write it here. It will automatically be disappeared. So I need to divide this by r factorial n minus 1 minus r factorial. This one and that one are gone. And if you look here, if I divide this by that, it becomes n minus r. Okay? So it means, if you take this to be common denominator, this one divided by that one gives n minus r, and then you have to take it and multiply it to its numerator, yes? So this becomes n minus r times n minus 1 factorial. And then, yes, I have it, so let me make it better. Yeah, it doesn't work. Anyway, plus the next one. Can you tell me what happens now? What I should multiply in this numerator after these explanations?
Multiplied by r.
Thank you. So I multiplied by r because I divide this in my head by that one. This one and that one are gone. R factorial divided by that one, it becomes r. And I have to multiply this r into its numerator, yes? Okay, but now what can I do in the numerator? You see I have this factor here and here, so it is in common. So if you don't mind, let me pull it out from the right hand side. So I open a pair of brackets, I'm pulling n minus 1 factorial out. The denominator is of course the same, I copy and paste that. But in the numerator, when I pulled this one out, n minus r and r are left. So I would write n minus r plus r. But you immediately see that n minus r plus r, this r and that r are cancelled. I am left with one n. That n will be multiplied by n minus 1 factorial, and this will give you what? N factorial, yes? And in the denominator I have r factorial, n minus r factorial. And this is exactly the formula of nr. N choose r, and that is equal to the left hand side. So analytic proof of that was actually very simple. Now can you cook up a story so that without doing all this algebraic mess we can be convinced that this should be the case? I start writing something, might be it is a helpful hint. I consider n people. Okay, and look here, you have at least an idea of the left hand side. What is the idea of the left hand side? The idea is that among these people I choose R of them. Okay, so I would say that Rn, the number of ways that one can choose R people. Okay, but I hope that you can see what is going on. Do you see the story?
We are choosing the same amount of people R from a smaller N group.
But you need to be very precise. Yes, the idea is more or less not wrong, but you need to make completely sure because you want to prove something. Yes, it's mathematics, it's not social science, okay? So by looking at these numbers, can you come up with a story? What's happening? N minus 1, n minus 1, R minus 1. Let me I draw this circle. Any ideas? So in this choice of R people, there are two possibilities regarding this last person. For example, what are the possibilities?
He's chosen and he's not chosen.
Yes, exactly. So this is clear. When I choose R people from N people, there are some combinations that this people is involved. There are some combinations that this person is not involved. Sorry, this person is involved or not involved. So, and then it's clear if I know how many combinations are including the last person, and on the other hand, if I know how many combinations are excluding the last person, it's clear when I add these two numbers, it becomes the total number of choices out from this n many people, yes? This is the only thing that I want you to understand. So I would say that I can partition this number into an is included, an is excluded. Let me give the number of items here to be n1. Let me write capital N not to confuse it with this little n. And then let me put the number of items in this is n2. Let me tell you something first. What can you say about n1 plus n2 and its connection with this number? What is the relation between n1 plus n2 and this number that I am just circling right now? They are the same, yes. So don't hesitate, please. So n1 plus n2 is equal to nr. Now, can you tell me, forget about these problems, let me find a formula just for n1. In n1, you are calculating R combinations, but you want to have an. This is This is a have to. So in principle, you have R choices, but if you want to have a n included, how many choices are left for you? Come on, say something.
R minus 1.
Yes, R minus 1 from how many people?
N minus 1.
N minus 1, because an has already been chosen. I want to choose R people. A1 is chosen. It means that my duty is to choose R minus 1 rest of the people, okay, the rest of them. But I have n minus 1 people left, because if I write n, it means that I might happen that I am choosing an twice, which is not possible, and this is not meaningful. Okay, and what is n2 this time? Can you tell me? an is excluded. So how many choices I have to do again? Because an is excluded.
We still get our number of choices, but we can choose from one fewer number of.
Exactly. Thank you. So we are done. So on the one hand, I hope that you understand this argument. n1 plus n2 should be this, but n1 and n2 are individually this. If you put them, then I am done. Instead of n1, I put n minus 1 r minus 1. Instead of this n1, I put this. Instead of this n2, I put the other one. And on the right hand side, you see I have this. So that is a combinatorial argument for proving the Pascal identity. Okay? Is that understandable? Good. How many problems? Okay, there are 2 problems, and I think we have time to solve them, or I don't know, we can keep one of them for the future. So for example, compute the exact value of the following expression. So this is probably horrible, even if you want to do it with calculator, because I have to calculate all these things up to here. Okay, so I think, let me explain this one, and then I will keep this one for the next time. If you want to think on something, this is a good problem to think. So, of course, here you see, let me write the Pascal identity in front of your eyes. So the Pascal identity is this. If I have n minus 1, r minus 1, plus n minus 1 r, if I have 2 combination to choose numbers with these properties, these numbers are the same, these numbers differ by 1. According to Pascal identity, I can add 1 unit to this top number and write it n, and between these two I choose the bigger one. This is not something strange. I just proved this for you in 2 different ways, Pascal identity. But the problem is that this problem is not exactly the Pascal identity. For example, is this a Pascal identity? No, because they differ by 1 and they are equal. So this is not a Pascal identity, but the trick is this. The trick is, first of all, do you agree with me that 2 choose 2 is equal to 3 choose 3? Do you agree with this one or not?
Yes.
Yes, because 2 means 1. I have 2 people, I want to choose them, it is 2. I proved for you that n is always 1. So if I ask you what is this number, it is 1. 3 is also 1. So no matter, you will see why this is useful. Instead of writing this, I would write this. So that question mark is equal to, instead of 2, I would write 3, and then the rest of the story. 3, 2, 4, 2, 5, 2, etc. up to 99, 2. But can you see the trick? Now do you see the Pascal identity? Yes, the Pascal identity appears for the first pair. Yes, because these 2 numbers are equal. These 2 numbers differ exactly by 1. So I can combine these 2 into one choose number. How should I write that? Remember the rule. What is the rule? I need to add 1 unit to the top number. So instead of having 3, it becomes 4. And among these two numbers, I have to choose the bigger one. Between 2 and 3, the bigger one is 3. So hopefully you agree with me, according to Pascal identity, this pair can be replaced by that. Is that understandable?
Yes, and
And
replacement also drops.
exactly. Then the trick is this one. Now this new one with this next one is a Pascal identity. Why? Because the numbers on top are the same, the numbers in the bottom differ by 1, so if I want to combine them, I can. How? I write 1 unit more here, so it becomes 5, and between these two, I choose the bigger one, which is 3 again. And then, of course, the next one. What is the next one? The next one in this series is 5, 2. And then you immediately see that these two become another Pascal identity. So this time it becomes 6 and 3. Okay? And then, of course, if you continue in this way, can you tell me what is the last number? 103, yes. And now 103 is not hard to calculate, yes. I need 3 factorial in the denominator, multiplication of 3 consecutive numbers. Yes? And let me use my calculator. So 100 times 99 times 98 divided by 6, yes? Because 3 factorial is 6, so the answer is just simple. You see, even if you are not supposed to calculate, you were able to combine all these terms into just one single combinatorial number. So that is actually a powerful identity when it comes to combinatorics. Okay, I would recommend you to try to solve this problem. Of course, you can use your calculator to calculate each one of them and start calculating each one of them and see which one is equal. That's not my goal. Assume that you don't have any calculator and don't want to do calculations, just you want to use the Pascal identity to find the correct answer. How do you solve the problem? Okay, so I will thank you for listening. I will stop.